Hey guys! So for today we're going to do part 2 of chapter 14. We're going to start with titrations. You will be doing a titration simulation this unit, okay? So a titration is a substance where you have a known solution with its concentration, and then you have an unknown concentration solution. Now, these are generally acid-base reactions. If you take AP Chemistry or Chem 2 later on in college, you will probably do other types of titrations. But the focus of today's is an acid-base titration. So normally, you put the one you don't know the concentration of in the flask. So in this case, it's the acid because we've got the hydrogen ions in the solution. Then we put the base in the burette, or the one we know. This is called a burette. They are a little different because they read down. If you look, you drop the base in, and they start turning this pink color. When they're all pink, the whole flask, then we've hit equivalence. So what you need to know about equivalence point, so I would write, I know it's long up there, the equivalence point is when moles of H equal the moles of the OH. Because it's an acid and a base, when moles are equal, we've hit equivalence. Now that pink color that it turned was because we'd added an indicator. Now there are lots of different types of indicators. We generally do use that clear to pink one. It's just a dye that tells us the acidity of the solution. So it'll change when our pH changes. Again, lots of different indicators if you take AP Chem or you have to take general chemistry in college. Then you will see different kinds of indicators as you go through that. So here's what real life pictures look like. We go from clear, you drop some of the drops in, it starts turning pink, but you have to swirl it as you're doing it, and they swirl out. So then it goes back clear until you've added enough hydroxide that it's all pink. This specific indicator is called phenolphthalein. You don't have to know that right now, but it is important because that is the main universal indicator that people generally use. So we're going to do some titration calculations. Now, what I want you to write, I don't want you to write any of this yet down. I want you to write if H to OH is 1 to 1. So if they have the same value, then you just use MAVA equals MBVB, which is just a dilution equation. If they're not 1 to 1, then you have to do stoichiometry. Okay. That is one word. Sorry, when I erased it, it got smaller. All right, so we're looking at this equation. So remember, we need to think about what this problem makes. So I mix HCl. Okay, so we've got our hydrochloric acid, and we're adding it to sodium hydroxide, so NaOH. Remember, these always make water. And then whatever's left in this case will be NaCl. Okay, so this is balanced. So this is a 1-to-1 reaction. Remember, if it's 1 to 1, we can do this. Okay, so I've got Ma, I don't have. They gave me 10 milliliters. They gave me 0.1 molar for sodium hydroxide and 12.54 milliliters. Now, I have seen people are like, how do I know which one's which? The base is OH, the acid starts with H. So I'm going to move this down here, divide by 10 milliliters. I get that the molarity is 0.125 molar for HCl. Now remember, sig figs do matter. I understand the calculator says 0.1254, but there's 3 sig figs in our 0.100 molar, so we keep 3 sig figs. All right, I am also going to work the other one, which is a little rare, but this one is not 1-to-1. The way I can tell that is there are 2 hydrogens right there, but only 1 hydroxide. Okay, so I'm going to write my formula. H2SO4 plus KOH yields water plus K2SO4. If you need more practice on the product writing, let me know and I can send you some. It's not balanced. I need a 2 here and a 2 here. So we notice there are coefficients, so it's not 1-to-1. So we need to do solution stoichiometry. Now remember, we do solution stoichiometry with volume, but it's the volume that we have the most information about. So I'm going to start with this 22.87. Now, while the 20 milliliters was a volume, we did not have any other information about it. So we can't use that one. Remember, molarity split. So molarity is moles per liter, and it's always 1 liter when you split it like this. So 1 liter goes on the bottom, and then the molarity goes on the top. So 0.158 moles KOH. Now, oops, that's not done because we don't need moles of KOH. We need to get to moles of H2SO4. So this is the mole ratio. Oh, I have them switched. Sorry, y'all. H2SO4 is on top because it's 1 over given. And there are 2 moles of KOH for every 1 mole of sulfuric acid. This is where we stop because we're trying to find molarity, which is moles per liter, so I need to solve to moles. And I get 1.81 moles. Now, it's not moles, it's millimoles. Now, the reason I'm working in millimoles is because liters canceled for KOH, but not the milliliters. So I keep the millimoles, and then I do divided by 20 milliliters, and my millis will cancel out. And you should get 0.0903 molar H2SO4. Now you may have gotten 0.0905. That's because you just typed in what I wrote over there, but I left my number in the calculator. Now just remember, it's fine as long as it's multiple choice, just don't pick none of the above. All right. Now we're going to talk about strong and weak acids, and then we're going to do strong and weak bases. So a strong acid is one that completely ionizes. Now if you remember, ionize means it breaks apart. So it's one that breaks apart completely. Every time it says ionize, it means breaks apart. So a strong acid breaks completely. Also, this will have a single arrow when we have it in an equation. A weak acid will only break partially or does not break completely. With that, we get a double arrow when we write them in a reaction, which is why you've started seeing both of those, both a double arrow and a single arrow. So here's a strong acid indicated by the single arrow. While we're here, we're going to talk about conductors. Now, we've kind of talked about them before. We did have that lab that went through it. A conductor is something with ions in it. So pure water doesn't have any ions. So pure water is not a conductor. So here you can see the pure water does not conduct an electricity, but this strong acid does. So what I want you to write is that a strong acid is a strong electrolyte. Okay, strong acids are strong electrolytes. Always, that's how it works. Okay, I need you to write this table. Like, this table is super important. There are 6 strong acids. You do need to memorize them. You have to know them. You need to write them on your periodic table. You need to write them in your notebook. You need to commit them to memory. Okay, these 6 are very important. That's because there's hundreds of acids out there, maybe even more. but only these 6 are strong. So if you know these 6, then everything else is weak. Now up top here, they're just talking about mono and diprotic. Mono just means 1, and di means 2, so that's how many protons they're losing. So if you look, 1 proton, 1 proton, 1 proton, 1 and 1. But this one has 2, so it's diprotic. Sometimes we also call this polyprotic because there's more than 1. You have to know these 6 strong acids. All right. Weak acids, like I said before, they've got this double arrow. They only partially break. So in the picture before, everything broke into ions. In this picture, only one of them broke. Very, very small amounts break. For this one, a weak acid is a weak electrolyte. And you can see that here. Weak acids are weak electrolytes. They just very dimly light that light bulb. Okay, so here are some table of some common weak acids, but you don't need to memorize them because everything is weak except those 6. Hydrochloric, hydrobromic, hydroiodic, sulfuric, nitric, and perchloric. Those are the only ones that are strong. All right. So what this is doing, and there are some mastering problems on this that are commonly missed, so I just want to go over it. So we're talking about what does HCl break into. So HCl is a strong acid. So it breaks into H plus and chloride. Now because it's strong, and that means it completely breaks, the concentrations are equal. So this is 1.5 and this is 1.5 because it completely breaks. If it does not completely break, like this weak acid, they have double arrows. They still break, but not all the way. So while this is 3 to start with, this is less than that because it doesn't break completely. Just breaks a little bit, so it's going to be less than. So strong acids break completely. So strong acids break 100%. That's what I'm going to write. Weak do not. All right, so here we've done the first 2. You need to identify, is this strong or weak? It is strong. So this, the H plus concentration, or H3O plus, will be the same value because it's strong. Now here we're looking, this thing is weak. If it is weak, the hydrogen concentration is less than the original amount. Okay, so this is A. For B, B is strong. So not good brackets. So it's equal to. And then C is weak. So weak ones are less than. Strong ones are equal to. That's what you need to know. Now we're going to talk about bases. As far as the bases go, I do not need you to write this table because there's more than that. I need you to write for strong bases. They're the same definition as strong acids. They completely ionize. Dissociate means the same thing. They break apart. So they completely break apart in solution. Now the strong bases are group 1 and 2 hydroxides. So while the ones in this table are group 1 and 2 hydroxides, there are more than these 6 that are group 1 and 2 hydroxides. Okay, then down here at the bottom, remember acids break 1 at a time, but bases don't. Bases will break completely. So all of these over here where there's this 2 subscript, they're going to break completely into 1 barium and 2 hydroxides because of that 2 subscript. Acids do not do this, only bases. All right, so as we see in this slide, the strong base of NaOH, which is a group 1 metal, will break all the way into sodium ions and hydroxide ions. All right, weak base is similar to a weak acid. They're going to use the double arrow. They only break a small amount. Dissociate very small, or does not completely break, something like that. They're just like the weak base or weak acids. So here you can see only this piece broke. There were 5, only one of them broke apart out of the 5. All right, so here are some common weak bases. The only one we really use a good amount is going to be ammonia, which is NH3. That is a common name, but I need you to be okay with that. So if you need to write in your notes, ammonia is NH3, and that is weak base, that's fine. I will tell you, for weak bases, you always have to add water to them, otherwise they don't produce hydroxide in solution. All right, so now we're doing what we did with the acids. You need to think, is it strong, is it weak? So K is a group 1 metal, so it's strong. So KOH will break completely with a single arrow into K plus and OH minus. Now they're looking for the hydroxide concentration. If it breaks completely, it is equal to the concentration of the original base. Now for this one, so we've got methylamine, which is a common weak base. We add that to water. Also, it doesn't have hydroxide. That's the easiest way to tell, hey, by the way, this is weak. Okay, I can't erase that apparently. Having a hard time. Okay, whatever. That's how it looks. They will produce, so this one will shift here. CH3NH3 plus our hydroxide, so we get that hydroxide concentration. Now because this is weak, this is going to be less than that amount. So it'll be less than 0.35 instead of being equal to, just like with the acids. All right, so we've done A and B already. Let's do this one because this one's important. So this is a strong base, that's group 2 metal. So strontium has a 2+ charge. It breaks into 2 hydroxides. Now remember what I talked about with bases. So because this is normally equal to, but now I've got a 2 coefficient, I have to times that value by 2 before so this is my answer because it is equal to, not less than, but because there's a 2 in front of that with the coefficient, we have to multiply by 2. Okay. So the only one you have to multiply by 2 in this one is here. So this would be 0.11. This one is less than, so it's just less than the 1.05. And this one is equal to because that's a strong base, so 0.45. I don't know why my eraser is not working now. I have no idea what's happening. Okay. Last thing, just remember water's amphoteric. Amphoteric means it acts as an acid and a base. Water is not the only compound that's amphoteric, but it is one of the most common amphoteric substances.